Hey, Vlad here, devinsideyou.com. Welcome to another video. This is going to be the last video in the Monads series, but as I mentioned in the beginning, I'll create an entire functional programming playlist in the future and tie this one in there somehow. Today we're just going to tie some loose ends and also play around with some very common monads. Let's get right into it. As always, we're in the Ubuntu virtual machine and we're running Sublime Text fully maximized with a plugin called Terminus, which emulates the entire terminal for us, which we use to run SBT, which we use to rerun our main function every time we save the file. In fact, let me start doing this right now. Let's go to main. Let's start running it again. And also, I've been running out of space all the time. So what I'm going to do now is I'm going to split it into 2 panes instead of 3. So I can go here, I can destroy the one underneath. And yeah, that's pretty much all I wanted. So let's go to point program. Close out the tabs. There we go. So the first thing that we're going to do today is we're going to go to our for comprehension. By the way, I'm gonna remove the laws. We don't really need them anymore. So I'm just gonna remove that like this. Okay. So we're gonna go to the for comprehension and we're going to refactor this part a little bit. So I'm just gonna go over here and I'm gonna create a private def, which is gonna be called from input to message. So input comes in, which is a string, another string comes out. And it's going to be this entire code like this. So I'm just gonna paste that over here, and I'm gonna put a bunch of vowels in front, and I'm gonna go over here and I'm just gonna return the message. Okay, let's see if it saves. Yes, it does. Okay, so now I can just go over here, put it over here, feed it the input, and remove everything in between. Okay, so now it looks like this. Also, we could obviously, we could play around with this. We could take this one and inline it right there. So now you see only the class decomposition. Also, what we could do is we could say, let's ignore the input. Let's go straight to message by just taking the prompt classly and just mapping it to from input to message, right? And now over here, we already have the message, right? So monad laws, or in this case, a functor law, allows us to do that. Which way do I prefer it? I think I prefer it like this. Yeah, I think like this is better. We can also see if we can go and improve this one. Yeah, maybe we should improve that one as well. I'm not sure if we're going to use it actually today, but at least it's going to look less ugly. So what we have prompt class like flat map input, and we have this entire thing over there like this. And also remove that flat map like that. I'm just going to remove one of these braces. Okay, so now we just need a message over here, and we're going to get the message by just calling from input to message like this. Okay, so Scala form is going to indent it properly. Yeah, so it's exactly the same code, so it's not as ugly as before. Let's go back to the for comprehension like that. There we go. All right, the last thing of the refactoring is that I don't want you to start thinking that it's a common practice to add this classly suffix to methods. So what I'm going to do is I'm going to go and I'm going to remove the regular display, right? And I'm going to remove the regular prompt. Kind of want to keep this line over there. And I'm also going to remove the comments like this, and yeah, there we go. So it should still compile, and now I'm just going to remove all the display classless with just display, and all the prompt classless with just the prompt. Okay, so now you can read it even better. Okay, so just display hyphen, display question, prompt, display from input to message input, display hyphen. So we have a tiny for comprehension. Cool. All right, so as I mentioned in the previous video, what we're dealing with today is this. So if we put something invaluable over here, the convert string to int function is not going to be able to do that, and it will throw an exception right over here. So if I scroll up, I'm sorry, then something somewhere should say that it happened at line 48. Where is it? Over here. All right, so this is exactly where it exploded, line 48. So we're going to use monads to help with that. Let me revert it back to 5. Okay, there we go. Now, Scala already has a built-in type to deal with situations like this, which is called option. But we're going to build it from scratch because it takes only a few minutes to build it from scratch. And this way you will see all the code and you will see the entire monad. So what I'm going to do is I'm going to create a new file. I'm going to save it. And now I need to make sure that we're saving it into the functional programming library, source main Scala. Okay. And I'm going to use the naming convention from Haskell. So in Haskell, option is called maybe. So this is what we're going to do. Maybe Scala. Okay, it's going to be in package fp library like this. By the way, another reason why I'm doing this is that so that you can see that some monads are really different from each other, but they all can be sort of slammed into this one tiny interface of flat map. Okay, so what we're going to do is if I type ADT and I press tab, then it will generate a algebraic data type, but I want to use an abstract class over here, our ADT is going to be called maybe, like this. Okay, and this maybe is going to be parameterized with some a. Okay, and we're going to have two implementations. We're going to have a final case class in Haskell, it's called just, and in Scala it's called sum just. Okay, and there will be some value a, right? So this value is also going to come from here plus a. Okay, and it extends maybe of a, and the other one is going to be a case object. In Haskell it's called nothing, and it extends maybe of nothing. I'm going to make sure that you understand that this is the Scala nothing, Scala built-in type nothing, because in the option algebraic data type is actually called none. So in you have option, sum, and none, and over here we have maybe, just, and nothing. Okay, so this is an option. Okay, there we go. We have quite a bit of code to write today, so I'm just gonna advance a bit faster than usual. So we're gonna go to IO, and we're going to take the entire monad and just copy it, bring it down over here, and everywhere where we say IO, we're just going to say that this is going to be a maybe. Okay, so how do we create a pure of maybe? Well, we just call just. Okay, this is the same code basically. I don't think that it's a big deal that this is a by name parameter here and it just doesn't have a by name parameter. I think it's going to be fine. All right, then in map, how we're going to create it, this is what I meant. Like it's gonna look like quite different from this one. So in map, for example, let me actually copy that, and we're going to implement it over here, right? So the implementation of all the map and flat map and all the other methods in maybe is gonna look it's gonna follow like the same sort of skeleton. Okay, so we're just gonna take this and we're gonna say, I'm sorry, not this, we're gonna take CA and we're just gonna match it, and then we're gonna say, okay, is it a just a, then we will do something, and otherwise if it's a nothing, then we will do something else. First of all, if it's a nothing, then what can we do? Well, we can't really do anything, so we're just going to return nothing as well, right? Because we need to produce a maybe b. And if we have a value a, then what can we do? Well, we already use CA, we only have a b. Well, let's call a b with a. What is it going to produce? It produces a b, but we need a maybe, so all we need to do is we need to call pure, right? Pure, or we could also call just, but I'm going to write pure. Okay, the next one, so see it's like totally different from this one, but it still fits the map signature. So let's just continue. So if we have flat map, it's gonna have basically the same code. So I'm just gonna copy that. I'm gonna paste it in over here. So all we're gonna do is we just don't need to produce this pure, right? Because it already this ACB function, ACB, it already produces a maybe b. Okay, and the last one is flatten. It's going to have a similar pattern match, right? All of them are going to have this pattern match. Okay, like this. Paste it over here. Then we're going to see, okay, so is it a just a? Technically, this is going to be a maybe a, right? So this is an MA. So we just strip out the just and return just the MA, and that's all. This is flatten. And if I didn't do any typos, I did. This one is called CCA. Oh yeah, this is the only typo, right? So I just copy pasted it from there, right? So this is the implementation of the entire monad. You just pattern match, and then if it's a just, then you do something with it. Otherwise, if it's a nothing, then you don't do anything. And by the way, this is one of the things that that monads are good at. They encapsulate some sort of behavior, right? So the option monad basically encapsulates the behavior of whether to run some code or not to run some code, right? So this is almost ideal for an exceptional kind of behavior. So now we can go back and we can start using it. So if we go over here, where we're converting the string to it, well, we're just going to say that it's not going to be int. We're going to say that it's going to be a maybe int, right? Maybe int. And how we're going to do this? Well, we're just going to use the regular try catch block. I'm just going to say try, and we're going to try to create a maybe just of this thing. Okay, and if it doesn't work, then we're just going to say catch, and we're going to say whoops, catch like this, and we're going to say if the number format exception is going to happen, well, then we're going to produce a maybe nothing, right? But now the rest of the code is not going to compile because maybe just create some more space over here like this, right? So now it says at line 27, where we're using this function, right? Line 27, it says, hey, I wanted an integer, but you gave me a maybe an integer. One of the sort of benefits that you get from functional programming is that the type system constrains you a little bit. So over here you see, okay, we're in a very local function. So all that we can do is we can if we decide to change the signature, right, then we will have to keep going. You know, like if, for example, we wanted to say, okay, then because we're not always sure that we can get a number, then maybe we cannot always get a string out of it. So if you start changing the signature over here, we would need to keep going the call stack and also keep changing the signature. So in this case, we're lucky and we don't really need to do that. We can just manufacture a string in this failing case, and in our case this is going to be enough, because what we can do is we can say, okay, if you didn't put a valid number in, we're just going to display an error message, right? So we were lucky that we can just produce a string, and this is what we're going to do now. So what we're going to do is we're going to say that this is going to be a maybe integer, right? So I'm going to say over here this is a maybe integer, right, which is a maybe int, and we're going to call it like this. Okay, so now what we can do is we need to produce a message somehow. Okay, so I'm going to have a val message, which is a string, and we're going to have some implementation in just a few seconds, and then in the end we're going to return this message. Okay, so how we're going to implement it? Well, we just pattern match again, right? So for example, over here we can say that it's a maybe integer match. Okay, now we can say case maybe just, and now I'm going to call it like this, integer amount, right? Then I don't need this val, I just need an arrow to the right over here, and I can bring this code up so that it will do the same thing as it did before. So in this case, it will produce a message and return it, and otherwise, if it's a case maybe nothing like this, well, then I can just produce a different message. Okay, so I'm going to say val message equals, for example, sorry, need a valid number like this, and I'm also going to return a message. So both branches produce a message, and the entire method also produces a message. So now everything should compile. All right, so now if I go and produce some crappy value like this, we're just going to see, sorry, you need a valid number. And by the way, let me fix it again. Notice that this method technically says that whatever happens, I'm going to return you a maybe. But remember, we're in Scala, and Scala has nothing. So if we throw an exception somewhere, the compiler is not going to be able to detect that, right? So for example, if I go over here, right, or for example, if I have some side effect like print line high, and or if I just throw an exception, this error, blah, right? So it's gonna explode, right? So I'm just pointing out that it's a common sort of false benefit of functional programming is that people say, okay, like I feel like if my code compiles, then it's doing the right thing. Well, it doesn't always do the right thing. It's just that it's more likely. Okay, so I just wanted to point this out, right? So don't trust the function signatures. This is all I wanted to show you. Okay, there we go. Okay, everything is fixed now. Notice that in our implementation now we're doing three things. The first one is figuring out if the maybe is a just or if it's a nothing. The second thing is transforming the input, the integer amount, into a message. And the third one is ripping out the message out of a maybe, right? So we had a maybe and somehow we ended up with a string, right? Maybe to string. Now this is too imperative. There is like all of this code happening at once. Let's make it a bit more functional. Now maybe has a monad, and a monad is also a functor, and therefore there is map defined on it. One of the things that we can do is we can split these steps, and we can say, okay, there will be an intermediate step where we transform a maybe integer into a maybe message. So this is going to be a maybe message, right, which is a maybe of string. Whoops, like that, and now we can say maybe integer, and now we can map it, and now this is going to be the integer amount, right? And what's going to be inside of there is this code, right? So you can just gonna cut it out like this and paste it over here. And now we can just go over here. We already used maybe integers, now we can just use maybe message. Now this is going to be message, right? So if the message is there, well, we're just going to return it, right? Because we need to produce a message over here. And if the message is not there, then we're just going to return that. Right, so I'm just going to do this like that. There we go. So this is essentially the same code, but now you can see that there's a transformation over there. Okay, transformation, and then just the figuring out if it was there or not. We can improve this code even further by introducing some helpers into the maybe directly. So for example, this code basically it just either gets the value or otherwise it returns a different value. So we can have a function called get or else, which is also present on option. We can just add it over here like this. All right, so we can just define a method here. It's going to be a final def get or else, And because of covariance, we have to do this covariance dance. We can say it's not just going to be an A, right? So there will be some alternative, right? Alternative, and it's going to be a by name parameter because sometimes it's not going to be needed, okay? And it's going to produce this super, right? Which most of the time is going to be an A, but sometimes not. Okay, so all we need to do is we need to match, same as always. We need to say if it's a maybe just A, then we just return the A, and if it's maybe nothing, then we return the alternative. All right, let's see if I made any typos. No, I didn't. Right, so this code is essentially exactly, in fact, maybe I can do this. Okay, so program. Right, so this code is essentially exactly the same code as this one over here. So now, instead of that, I can just say, to copy that, okay, I can say maybe message dot get or else, right? So it's either going to get the message or it's going to produce this string like that, right? So this is essentially exactly the same code. And also it's a very common pattern to map a maybe or to map an option and then to retrieve the value. So we're going to have yet another helper, which we're going to call maybe or else. And in fact, in Scala, it's called fold. Let's create some more space over here. And I'm going to say final def map or else. And this or else can now be just a B. Okay, and this B is going to be, it's going to be the same as before, alternative, right? But it's now a B, and it also has the mapping, right? A B, right? So this part is going to be for map, and this part is going to be for the or else. Okay, so and then in the end, we're forced to produce a B. So now I can actually just clone this pattern match like this, put it over here, and now I just need to use the function here, ABA. Okay, so this is going to be a map or else, and now we can go over here and we can say, instead of map and then get or else, we can just go and say map or else, and then as the first parameter, we're just going to put the string inside. Okay, and now because there's, you know, or else, it's not going to be a maybe string, it's actually going to be a string. Right, so this is the actual message, right? So we don't need the extra get or else part over there like this. Okay, so now we can actually go and inline all of this stuff. So for example, we can say convert string to int and then map or else like that. Okay, and we can just return this thing, right? And the whole thing turns into an expression, right? So this entire code is now, you know, it feels a bit more functional. In fact, we can also extract this into its own method. So this one is called from input to message, but we can also have from integer input to message, right? So I'm just going to go down, have it over here, right? This is what functional programming gives us, this easy refactoring, right? So we can say from integer input to message, right? And we can say that this one is called integer amount, and it's going to be an int, and the implementation is essentially this code over there, right? Like this, and we need curly braces over here, like that. So now we can just use this function right over here, like this, right? So add expansion is going to convert this def into a function, right? Let's see if it made any typos. No, it didn't. And over here, we can also start inlining thing. For example, positive amount is used only over here, right? So we can just cut it out, put it over here. Balance is used only over there. Cut it out, put it over here. Message is used only over there. So we can just remove all of these vowels. We don't really need them. And now we also don't need curly braces. And our code gets smaller and smaller and smaller. Now this is not easy to read if you don't know, you know, if you're not used to this functional programming style. But if you are, then it's really nothing special. Now we sort of got lucky that we didn't have to fight the compiler. You know, in both situations, producing a string was fine for us. Okay, but what if we need to? What if we needed to alter some more behavior? What if we had to go up and decide to run this code again, for example, until the input is valid? Well, not a big problem. Just going to duplicate this one, okay? And we're going to change it from input to tuple, or tuple. I still don't know how to pronounce this, okay? So input comes in, and now, because it's going to be called in the for comprehension, we need to produce an IO. We need to produce an IO, and this time it's going to be an IO of the message, which is a string, and also a boolean, which is going to describe if things went well or not, right? So this thing needs to be a tuple, like this, okay? So what we're going to do is, and every time you're dealing with IO, the first thing you do is need to do IO dot create. Well, not every time, but basically because we're dealing with you know, by name parameters. Let me create a bit more space here so that it looks better, right? Okay, so what we need to do is the first line is going to be similar as what we had before. So we're going to have maybe integer, right? Maybe int like this, and it's going to say convert string to int, input. Okay, and I'm gonna throw an exception over here. I just want to see that it compiles. Okay, right, cool, it compiles. Okay, so now we're gonna have a message. So we're gonna have a message, which is going to be maybe basically it's going to be the same code as over here. In fact, I'm just going to call this. I'm just going to say from input to message with. In fact, I can't call this yet because we don't have the input. So what we need to do is we need to do that and then to take this code and do it again, right? Basically, so it's a maybe integer map or else this code. Okay, so let's see if it compiles, and it does. Okay, so now we also need to produce the flag. So we're going to call it was input valid, and we're going to say maybe integer is instance of maybe just, like this. And now all we need to do is we need to produce a tuple. Oh, come on. We need to produce a tuple like this. Message, arrow to the right, was input valid, right? So this is the tuple that we wanted to produce. And before we continue, we're also going to have a tiny helper inside of maybe. So we're going to go over here like this, and we're just going to say final def is just, which is a boolean, and we're just going to call is instance of maybe dot just, like this. And we're also going to have final def is nothing boolean, and it's just going to be not is just. Okay, so now over here we can just say is just, like this, is just. All right, so all we need to do now is we need to integrate it into our for comprehension. So first we're going to go and we're going to say we're going to unrefactor this. So to say, we're going to say give us the message, which is going to come from here like this. Okay, so this is the same code as before, and it should be an equal sign like this. Okay, so now what we can do is instead of using that, we can say from input to tuple, and now this is not a message, this is going to be a result. And remember, because this is an IO, we need to use flat map again, so we need to cut it we need to get it out like this. And now what we can do is we can just pattern match it. We can say message, and we can say was input valid, and it's going to come from result. Now in Scala, in option also implements with filter, and because we can't use it right away. So with option you would be able to say it like this, right? And you wouldn't need this line. Okay, but we actually need it. Okay, like this. So now what we need to do is in the last step, so we need to add one more over here. We need to say that I'm gonna have like some scope over here, and I'm gonna say, okay, if was input valid, well, then we can just create an empty IO, so to say, like this, right? So we're basically done. Otherwise, we can just create the description again with the same arguments, okay, like this. In fact, maybe Scala Reform is going to fix it for me, like this, okay? So, yeah, let's leave it like this. Okay, so now if I go and if I change this input to something invalid, where is it? Okay, over here, then we're gonna have an endless loop. So instead, I'm gonna have this, right, like this. Oops, not as a string, like that. Okay, so now if I put in a 5, everything is going to be okay. But if I run it again and I put ADF, I put something else, it's going to say, sorry, need a valid number. It's just going to keep running until we put a valid number like 123, for example. All right, cool. Let me go switch it back to a 5 so that everything goes faster, like this. There we go. Cool. Also notice that this solution is not necessarily tail recursive, and sometimes you can fix it by using the chains of flat maps instead of using the for comprehension, because the for comprehension introduces an unnecessary map. But in this case, I believe it's actually not even going to be enough. So in a proper functional library, you would make sure that your IO monad and all of your monads that they're stack safe by using techniques like trampolining, for example. I already made videos about that, but this is not important today. We're just going to continue. All right, so now I'm sort of in the process of convincing you that even though we're enforcing so much structure, we still can do everything that a regular imperative program would be able to do. For example, if we needed even more like from this, like for example, let's say that the user should only be able to input the incorrect input only 3 times, right? So we're going to repeat it only for 3 times. Well, it's not that hard to do. So what we need to do is we need to split that into another function, which is going to be called loop. So this is going to be called loop from now on. And the input is going to be not an array of string. We're going to say how many tries are left after this iteration. You're going to see why I named it like this in just a few seconds. Okay, so now in create description, all we will need to do is we will need to call loop, right? And we're going to say that this parameter is going to be 2. This is why I call it after this iteration, so that we don't specify the 3, we actually specify the 2. You know, we could improve this code indefinitely, but you know, because we're going to be comparing this against against 0, we need to start with a 2. So the second try is valid, the first try is valid, and the 0 try is valid. Okay, so now we just need to go down into our for comprehension, and we need to do something more in our if expression. So the first thing that I'm going to do is I'm going to press enter over here, so that this looks a bit more like an actual if-else statement, right? Okay, so there we go. All right, so if the input was valid, then you know we're going to do the same thing. But then before just running the whole thing again, we need to make sure that we have enough tries left. So before that, we're just going to say else if, okay, and we're going to say tries left equals 0, which means that there are no more tries left, and we're going to have another for comprehension over here, which is going to, you know, yield this, because you know we somehow need to produce an IO unit. And now we can say over here, well, let's display something else. Let's say you ran out of tries, and let's also display hyphens. Display hyphens like this. Let's see if I made any mistakes. Create description. Yeah, okay, over here we also need to call loop, and over here we need to say that we're calling loop with tries left after this iteration, and we need to subtract 1, right, because this iteration already finished. Okay, so this is the same code as before essentially. Let's go and do this part again. In fact, you know what, I'm gonna do that and that and that, and this way I can just uncomment this one. Okay, like this. So let's say we're doing 1, we're doing 2, we're doing 3, and now it says you ran out of tries. And we do it again. Let's do 1, for example, and now we're putting a valid number in. Bam, we have everything's working. Cool. Now let's switch to this one again, so that everything works faster. Let's go up to our for comprehension, and it doesn't fit into our screen anymore. Let's do this. All right, so our for comprehension gets a little bit bigger, but it's still, you know, it's still okay to read. In fact, a bit later in the video, we're going to refactor this, and we're going to put it into its own function. Now, I want you to focus on this last line over there. In fact, there are multiple things that are happening over there. So instead of just doing this, I'm going to say that the next state is being calculated, right, which is this code over here, like this. And also the next value is being calculated, which is the IO of the unit, right, which is loop next state, and then the next value is being returned like this. Okay, so next value is being returned. Okay, so this is exactly the same code. Now what I'm going to show you next is going to be a solution to a problem that is not super clearly visible over here, because this is just a toy example. It goes by the name of the state monad, and contrary to its name, it doesn't store the state for you, it stores the state transition for you. Now, as I just said, a proper state monad demonstration requires a big example, and I'm sure that I will create a video dedicated to the state monad alone in the future, but for now we're just going to continue. I'm just going to create an even simpler example so that you see the mechanics of the state monad, and then we're going to come back to this one. We're going to start using the state monad over here, but in fact the code is going to become ugly, which is kind of ironic, because the state monad, in fact monads in general, you know, they're there to make the class decomposition more affordable, right, so that less syntax is needed, right, but in this case it's actually going to get worse. But I really wanted to show you the state monad, and I couldn't figure out how to tie it into this this example. So we're going to start with a smaller example, and then you're going to understand what the state monad is doing, and we're going to actually implement the entire state monad, which is just going to happen in a few minutes. So what we're going to do is we're going to go into the interpreter, right, and we're going to comment everything out, and we're going to have an entire new example. And by the way, the state monad is one of those that are a bit tricky to wrap your head around it, because there's like one part of it which is like super weird, and I'm going to show you this. But you know, if you play around with it, it's actually going to become clear. Okay, so we're going to start with an example where we have a regular stateless function. It just takes an int and converts into a string. So the I comes out, and by the way, I'm using the functional syntax instead of the method syntax. Okay, so I comes in, and then we just need to produce a string. So I'm going to use a string interpolation. So all it will do is it will say I is, and it's going to say if I is even, basically, right? Then it's just going to say even. Otherwise, odd, right? So basically it just says if something is even or if something is odd. Let's see. All right, cool. So now what I can do here is I can say print line stateless of 0, and I can say 1 and 2, and it's going to say, okay, 0. Let's create a bit more space like this. Okay, let's save it again. Okay, so it says 0 is even, 1 is odd, 2 is even. Big surprise. Now, because I chose those rising numbers 0, 1, 2, you can see that there is a hidden state transition there, which can be described by a function +1. So if you wanted to keep track of this state transition, we would need another function. So I'm going to go over here. I'm going to say stateful. Right, so this is going to be a stateful function. So the stateful function is going to be a function that will take some initial state, and then instead of just producing the string, it's going to produce a tuple with a string and with the next state, right? And these are just going to be type aliases, right? So initial state is going to be an integer, and the next state is also going to be an integer, right? Because we're going from one integer to +1, okay? Okay, so what we need to do over here is we need to say the same thing. I comes in, and now the string is going to be produced by just calling stateless, right? And then the right part of the tuple is going to be the transition that we had here, right? So we were going from 0, 1, 2, so the transition was +1. So over here, I just need to say I +1, like this, okay? So now if instead of using the stateless function, we're going to use the stateful function like this. So I'm going to call stateful was 0, stateful was 1, and stateful was 2. Then on the left side, what we have tuples, right? We have T1, we have T2, and we have T3, like this, okay? Now, the point was that we didn't have to carry the 1 and the 2 manually, right? So what we can do is we can pattern match on that tuple, right? So we can say this is going to be the A that we're not going to be using. This is going to be the B that we're not going to be using. Whoops. Comma. And this is going to be the C, S, 3, like this. So now instead of manually carrying the 1 and 2, our state monad or our state function over here, it knows that it needs to do +1. So we can just go and reuse these S1, S2, and 3. So S1 is going to go over here, and S2 is going to go over here. Okay, so now what we can do is we can print it out. We can print out T1, T2, and T3 like this. And also I'm going to print out my hyphens, -u to 500 times 50. And usually when you use the state monad, you're dealing with functional programming here. So you want the same result to be produced if you give it the same state. So now these ones, they produce tuples, right? The first is the first value in the tuple is the string that we had before, and the other one is the next state, 1, 2, 3, right? Because remember, our function produces a tuple of the message and the next state. So now what we need to do is we need to build a state monad that will do this whole pattern matching on the tuple for us. So by the end of this, we will be able to write something like this. We will be able to say, okay, just get A out of stateful, and just get B out of stateful, right? And just get C out of stateful, and yield C, for example, right? So this code is not going to compile. And by the way, this is going to be this weird part about the state monad, because we're going to be using the same val 3 times, but there will be still like this feeling of mutation, okay? So let me comment this out, okay, like this. All right, cool. So essentially, we're building a monad around this function, right? So let me write it down. It's actually going to be a function that is going to be called run. There will be some sort of state, and there will be some sort of A. Right? So it's going to take an S and produce a tuple of A and S. Okay, so if we could implement this function somehow, right? We could by calling stateful, right? Then we would be able to define a monad for it. So let's go and do this, and we're going to actually do this by copying the entire IO monad. So we're going to copy, going to go to the IO monad. This is collapse now. I'm going to copy that. I'm going to create a new file. I'm going to call it state.scala. Okay, I'm going to paste it in, and everywhere where it says IO, I'm just going to say state. And I'm doing this to show you the similarity. All right, so if I go back to our interpreter with this function run, I can just copy run, and I can paste it over here so that you see it like this. Hold up, like that, and like sort of like that over here, right? So that you see that it's just that there's another parameter over here, which is S. Then this method is going to be called run. And now we don't start with nothing. We start with an S, and we don't produce just an A. We actually produce an A and an S. right? This is going to be our state monad. This is how the state monad looks like. Very similar to an IO monad, but it also drags some state around and it modifies it. All right, so now we're just going to go one by one, and we're going to say, okay, so over here we also need an S, and over here it's going to be a state of S and A. So over here we're just going to say, okay, some S is going to come in, and we're going to produce a function with an A and this S. Okay, so this is create. By the way, as soon as I'm going to start saving the file, nothing is going to compile, because one of the big problems that we have over here is that for the first time, our data structure that we're building the monad around, it has two type parameters instead of just one over here, right? So we're gonna have to deal with this, and for now, I'm gonna write some code that is not going to compile, but it's going to help you visually understand what is happening. So we're going to partially apply the type. We're going to say that this is not going to be a val, this is going to be a def, and the s is going to come here, and then the a is going to come from somewhere else. So it would be awesome if you could say this is going to be a state of s, and this is going to be some a that will be provided later. It's not going to compile, but I'm just going to still write it over here, so that you see what's happening, right? So this is, by the end, this is the only thing that is not going to compile, and then I'm going to show you how to fix it. All right, so the first thing that I'm going to do is I'm going to go to everywhere where it says state A, and I'm just going to mark it, and I'm going to say, okay, this is not going to be state A, this is going to be state SA, okay? Because we everywhere we have to drag this S along. We have to drag this S along. All right, so pure just calls create, right? So this is exactly the same code. Map is also going to be very, very similar. You really don't even need to think about it, right? So everywhere we say unsafe run, we're just gonna say run, but run needs some s, so we need to insert some s over here. Where is it gonna come from? Well, state.create, it wants an s over here. In fact, if you look at s.create, it actually doesn't want to deal with the s at all, right? So you give it an a, and it will do all of that. So what we need to do is, instead of calling state.create, we're actually going to call the main constructor state, which starts with this s, right? So instead of state.create, we're just going to say state. Okay. In fact, let me press enter over here, like this. Okay. So we're starting with state. Some s comes in. We have ca. We call run. We pass this s along. What comes out is a. Okay, so then we can call a b with a, b comes out, and this is how we can produce a state of b, right? So with flat map, it's going to be very similar. So instead of doing state.create, we're just going to do state, and let me press enter over here, like this. So we're going to start with some s, right? We call ca run with an s, like this. By the way, I just realized that we made a mistake over here. So if you run, I just read it from here. So if you call run and pass in an s, then an a will come out. But it's not just a that comes out. A and s comes out. Okay, so we're going to say that this is going to be an a and some sort of s1. Okay, so we're going to go down again, and we're going to say, okay, ca run, and this is where I noticed that there was a mistake. Okay, so we do s1, and this is where we're going to use s1, right? Because if you call, if we have acb and we're passing in an a, then a state comes out, right? So we can do run on that state, and run needs some other s. So this is where the s1 comes into play, and now cb comes out instead. In fact, let's do this. So this was cb, and this was b and s2, right? Like this. And what we need to produce is okay, this is the same code, cb dot, okay, this is this line. Okay, in fact, we need to produce a tuple. So I made another mistake in map. So we need to produce this tuple that goes from b to s2, and over here we're going to have a tuple that goes from b to s1, right? So this s1 is actually useful. Okay, so we're just dragging this along, right? So compare flat map and map. Now they look very similar. And flat map is also going to be very similar. So instead of state.create, we're just going to say state, and then some s is going to be coming in, and we're going to call run by passing this s. And now this is not going to be a ca, this is going to be a ca and some sort of s1, and now we can run it with s1, and a and s2 comes out. So this is exactly what we need to return, a and s2. Okay, so I probably made some mistakes over there, but hopefully that most of it doesn't compile because of this thing, right? So let's just assume that I didn't make any mistakes over there, and let's just fix this, and then if it doesn't compile, then we're going to fix whatever comes at us. All right, so we need to learn about partially applied types, or partial type application, which is very similar to function currying or partial function application. So first of all, maybe we'll get lucky if we just have to specify one of them, right? Because maybe type inference is going to help us out. So we're going to remove this one for now. I'm just going to comment it out. And so now we need to fix only this one. And the way we fix it is basically we're gonna have a curly brace starting over here. I'm going to press enter. And then we're going to have a curly brace at the very end, one of them, somewhere over here. Right. So now, where is it? New monad. Okay. So now over here in this place, we have access to s. So what we can do is we can create a type alias. We can say that this is a partially applied state of a. Right. So now we have both access to the s and to the a. So we can say that this is just a state of s and a. Right. And it's called partially applied type because a part of it comes from here and the other part comes from here. Okay, and now what we can say is that it doesn't return a state s, it returns just a partially applied state, right? So let's see. So right now it should compile. If it doesn't compile now, then it means that I made some other mistakes. So let's go and see. Okay, so it starts over here. Wrong number of type arguments for state should be 2. Okay, map, which is over here. Okay, okay. So I replaced all these state A's with state SA, so I also need to do the same with state B. So state B should be state S, comma B, like this. Okay, let's see what else. Okay, only 3 errors. The first one is wrong number of type arguments. Okay, so let's go to flatten, like this. So this is not just state, it's state of S, comma state, like this, I believe. I'm not sure. Let's see. Yeah, okay. Lucky. All right. So now this code compiles, but unfortunately, it's not enough to look up this monad. So if let's just go over here. So if I'm going to say that, let's say that our s was an int, and we're going to create a type alias for partial a, and we're going to say that this is a state of s a, right? So this is basically a state of int and a, right? Let me use int over here. Right, I just wanted to show it to you. Okay, so now if we're going to ask for the monad, we're going to say, give me the m equals, give me the monad for this partial type. I believe this should not compile, and it doesn't compile because every time you're dealing with implicits, you better specify the type over here. I believe, in fact, in Scala 3, you will be forced to specify the type over here, and there is a problem with this because in this area we don't have access to s yet, right? Over here, after this equal sign we have, but over here we don't. So we can't just go over here. Let me line this. Okay, so we can't just have a colon, and we can't just have like a brace over here like this, right? Like that, right? And we can't start, creating the same thing as we did over there, right? So we can't do this, and we can't say that this is going to be a monad for partial, right? So just from the syntax perspective, this is not valid. So let me clone this like this, duplicate it, because people actually figured out how to do this, right? So what we're going to have over here is we're going to say that this is going to be a monad of, and so now over here inside we can have the regular braces, right? And then we're going to have this partial state thingy inside of there, and after that we're just going to rip out this partial state, right? This partially applied state, right? So now we can take this type alias and put it in there, right? And we also need to surround this with curly braces, right? So we're going to have curly braces over here, and this is where we're going to insert this type alias like this, right? So basically we're creating a type alias on the fly, and then we're retrieving it right away. So now I can remove this like that. Okay, and this is going to be the equal sign in the end like this. Okay, so now if I didn't do any mistakes, where is it? Monad partial. Oh man, I hope that this one would work. Let's go down. It's probably because I have some other typo. Let's see if it compiles. No, it compiles. Let me collapse the monad like that. Let me try to put it over here. Maybe because it's like down there now. No. That's weird. Maybe if I help out with the types over here, maybe I can say that this is going to be a monad for partial. Like this, monad for partial. No, okay. Double definition. Let's just go back to the interpreter, and let me just paste it over there. Right. So now it worked. Okay. So now it worked. Cool. Oh man, just got scared. All right. So now we can remove it, and we can go back to improving our state because this kind of looks ugly. All right, so let me unfold it. So the first thing that we do is, because now we know about type aliases, we don't need to do this, because this is basically this is called an anonymous type, or an anonymous lambda, right? So it's like a regular lambda where we create something and then we're getting it right away. So we don't need this one over here. We can just use the same type lambda, right? So the entire thing from here to there, which is still ugly, but it's gonna work. Okay, so it works, everything compiles, and because it's so long, let's rename this partially applied thing to P, but it's still gonna be super long. Okay, so this is a type lambda. And by the way, type lambdas are going to become easy in Scala 3, but they're also going to be less necessary, because there will be other techniques that will almost make them obsolete. Actually, what we can do until then is we can use a wonderful plugin called Type Projector. So I already have it over here. It's called Kind Projector. I'm sorry. So all we need to do is we need to go and include it like this. So we just grab this and we go to our build file like this, and we only need to use it in the FP library over here. So we can just go here, settings like this, like that, and we can just use a comma over here, and we can just put it in like this, add compiler plugin. I believe that this should be enough. Let's reload the entire project. All right, come on. There we go. So now I can just do run again, and now instead of this whole crazy thing, I can do a similar thing that I wanted to do before, right? So instead of this, I can just say that it's going to be a state of s, and now I can use a question mark, which is going to come from that plugin, and everything will be fine, right? So we can even mix them like this. So I'm going to go here, state, and over here, like this. Okay, so now it looks more beautiful. Now we don't need those extra curly braces. Let's go down, curly braces like this, and now we can inline that, right? So now it looks it looks more close to the IO monad, right? So in IO we have a regular val, but now over here we have a def, because we need this extra parameter, but the rest looks very similar. Okay, it's very pleasant to work with this plugin. And also let me destroy the pane on the right, okay, like this, so that we have more space. Now let's go to the pane program again, sorry, to the interpreter again, and now we can use this for comprehension. So the first thing that we will do is we will create our state. I want to let's create it over here. So I'm going to say val state is going to be a state of int and string, and now it's just going to be a stateful like this, right? So we basically create a state. What does the state want? It wants a function like this, and stateful is actually exactly like this, right? So we can create this. We don't need this run anymore. We don't need those print lines. Okay, so stateful, I meant, hold up, stateful like this. All right, there we go. So this is how we create our state. And by the way, we don't need those initial state and next state. We can just say int and int, right? Like that. Okay, so now we have the state, and we can go to our for comprehension and use state in there, state like this. Okay, so now let's do that, and we can say that what this for comprehension will produce is going to be some new state, right? So it's going to be new state, and it's going to be a state of int and string, for example, right? So we're going to go to our for comprehension and do that. Let's see if it compiles, and it's not going to compile. See, look, it says value map is not a member of library state, and the problem is that in our it's a similar problem to the problem that we had to with the Kind Projector. The problem is bigger and goes by the name of partial type application, right? So this notation that this object-oriented notation that gives us this map, it wants a type of type with one hole, but our state has two holes, and so there is a contribution to the compiler called partial unification, and I believe in Scala 2.13 it will be enabled by default. So what we need to do is we just need to go to the build file and we need to enable it. So we have somewhere our Scala C options, and we just need to add it over here, and it's going to go by the name of -y partial unification, like this. So now that we have that, all we need to do is we need to reload our project, and I hope that it's going to be faster than previously. Okay, let's run, and I believe now it should compile. Now it has to compile a bit more, yeah, but now it compiles. So let's go back to our interpreter and see what happened. Okay, so this is our new state. Well, we just need to see it. So for example, we can take my favorite hyphens. Come on, like what the hell? Okay, I'm just going to do this. Let's go down over here, print line this, and now we can, for example, print out, we can print line new state dot run, and then initial value is 0. Remember, like in the beginning, we're starting with a 0. The rest is going to be done with a for comprehension, right? So we're starting with a 0. Okay. So now what we should do is exactly the same code as above if we were tracking the state as well, because now we tracked only the last state. We tracked only the C. For example, what we can do is we can go and say, let's track a tuple. Let's track a string, for example, right? And let's return ABC in the end over here, right? So now we will actually see the state transition. So before we saw like 1, 2, 3, and now we see the 1, the 2, and the 3. It's a bit confusing, I know, but basically the monad is doing this for us. It's just carrying over this S1 to S1, S2 to S2, and so on, right? So now we don't have to do it. We don't have to do it ourselves. Okay. Also, we could do it with a list. For example, we could say that this is going to be a list of string, and we're just going to create a list of ABC, and there we go. It's basically the same thing, but now it's inside of the list. Okay. So now we can actually go back and solve our actual problem. So I'm going to create another pane over here, and I'm going to throw the pane program over there so that you see, so that you have something to compare over here. Okay, so over here we have the stateful function. So let's go and create a stateful function out of this, because this is essentially exactly what was happening, right? It's creating the next state and it's creating the next value. So if I create a function around this, I'm going to call it the same way. I'm going to call it stateful, and it's going to start with an int, but it's going to produce a tuple of IO, unit, and an int, right? Compare these types, right? So instead of string, we're just using IO of unit, okay? And it's going to be equal to this tries. I'm just going to call it tries. Arrow to the right, open brace. The brace is going to close over here, okay? So this is just this stateful function. Let me indent it a bit better, like this. Okay, so now that we have the stateful function, we're going to create state. We're going to have state, which is a state of stateful, right? So it's going to be the state of the same as over here, right? So over here we had int string. Now we're going to have int and IO of unit. Okay, and now what we need to do is we need to just run it, right? So we do state.run. Run was this. Oh, by the way, I need to be careful here. I need to use this variable over there. Okay, so we're just running it over here, so it's going to go over there. And what comes back is a tuple, right? It's gonna come out with the next value and the next state that we don't actually need. So now we can return the next value. Okay, let's see if I made any typos. Of course I did. It is over here. I need to produce next value and next state. Okay, like this. Okay, cool. So now actually let's start running it. Where's our interpreters? Over here. So what we do is we're going to comment everything over here, going to comment it out, and we're going to use our program like this. Okay, so now it behaves exactly the same as before. We're not going to go through all the other erroneous cases. So let's improve this a little bit. The first thing is going to be to just take this function out of here and put it over here, right? And let's just say that this is a private lazy val. Let's see if it compiles. Yep, it does. Okay, so yeah, so as I said, like before we had just one call to loop, right? Now we're creating the state monad and we're calling run right away. So again, as I said, this is not the perfect example for the state monad. And also let's create a helper over here that will do this for us. So if you go to the state monad, then we can just help. We can just create two functions over here. One is going to be called get A, and the other one is going to be called get S. Okay, so both of them, they get S inside, right? The current state, they get it in, and this one is going to return an A, and this one is going to return an S, right? So both of them are just going to run, right? But this first one is going to just return the first part of the tuple, and this one is going to return the second part of the tuple. Okay, so now we can go over here. Yeah, we can say, okay, do we need the first part or do we need the second part? Well, we need the second part. So we're just going to say, I'm going to call it run A and run S. Run A, run S, right? So basically we can just say run A over here and we're just going to get the value, right? So we're going to have the value, right? And we can actually return it right away now. So it's not as ugly as before, right? So basically we had one line before. Now we also have one line, but it's a bit less efficient because we're wrapping into the state model just so that we call run. So sort of the benefits of the state monad is that first of all, it manages the complex state transitions for you. Now in our case, the state transition was super simple. It was just doing a -1, right? But it could be it could be multiple things. It could be something really really complex. So you can have this transition captured somewhere else, and the transition will be managed for you. And also, where's our for comprehension over here? We don't have it here because I sort of cheated. Because look, we're passing in some sort of state, right? But we're not using it right away. What we do is we're subtracting the 1. If you compare this to the function that we had in our interpreter over here, right? We some I was coming in, we were using it, and then we were calculating the next transition. And what is happening over here is that the tries come in, but we're not using it. We're already calculating the next state, and we're working with the next state. So I cheated a little bit so to make this look a bit better. So what we can do is we can say that we're not going to do this, right? So it's not going to be the next state. It's just going to be the same state, right? Tries, and now we will be forced to do something over there. Okay, so this is the next state is going to be tries. Well, actually, we still need the next state, right? So this is the next state, tries -1. So we can just use tries over here instead of the next state. Okay, like this. But now the behavior should change. Actually, you'll only see it if we actually run it with this. Okay, so now we're typing something wrong. We're typing something wrong again. And we're typing something wrong again, and we're typing something wrong again, and we're typing something wrong again, and we never see the state finishing because we're not transitioning it to the next state. We never do this. Okay, so let's put in something valid in there, and do this and do that like this. All right, cool. So now we need to go and to actually use a for comprehension, which is what I wanted to show you. Okay, so we're gonna have the state, and we're gonna have the next state, right, which is gonna have the same type, like this. And now we can use the for comprehension. We can say, okay, do this at least once, do this once, and then do the next one, and then just give me the next one. Okay, yield B. Okay, and now we can, instead of working with the state, we can work with the next state. Okay, so now if I break it again was that, like this, then we do it once, second time, third time, and it says you ran out of tries. Okay, so let's go back here like this. All right, and now what we're going to do is we're going to do some refactorings. Now the for comprehension here, it makes it look like as if we're doing like two things, but we're actually doing one. If you have seen my video about for comprehensions, I'm not a big fan of them because another way to write this is actually much shorter. So if we have this, right, it's the same thing as saying state, right? So this first one, even though it's the same val, okay, and then saying dot flat map, and then this is the underscore, right? State dot map b. There's no space over there. Okay, so this is exactly the translation of the for comprehension, right? So if I remove this, it's going to behave exactly the same way. But now, because we have the monad laws, this is stating that we're mapping to identity, right? So this is the same thing as mapping to identity. And because of monad laws, we can say, okay, well, there's no point in mapping to identity, so we can just do this, right? And now we can join the lines. We can also use the regular ones, right? And now we see that it's actually only one operation, right? So this one, it makes it look like as if there are two operations, but this one is actually more straightforward. It's actually much shorter. Look, it's so tiny, right? So for example, we could also inline the whole thing, right? We can just say this, right? And we can also say that. So we're creating the state, right? We're just calling flat map, and then we're just calling run. So I'm not a big fan of for comprehension. Sometimes they're useful, but sometimes they're not. Okay, obviously that was a bit too much, so we still need the state. Whoops, we still need the state so that we can say state dot like this. Okay, let me actually show you again that it actually still works. So we're gonna go over here, we're gonna go do like that, and I'm gonna do 1, 2, 3, and we ran out of tries. All right, let's do this again, like this, like that. Okay. The cool thing is that because everything is so immutable, right? We can just go and we can take this val, and we can just take it out. We can say private lazy val state, right? Let's also use the type, which is a state of IO of unit, and int. Oh no, the state has to be first, right? So it's int and IO unit. I always confuse them, right? Like this. So now we actually can remove this, and because it's an expression-oriented language, this is now just one expression like this. Okay, in fact, we don't even need this separation. Like usually what you will do is you would just inline this whole thing in there. We can do even more refactoring, like this whole thing, right? It basically is just a method that is going to be called decide what to do next. Okay, so if we're just gonna have a private def over here, decide what to do next equals this, right? We just need to make sure that it has the was input valid, which is a boolean. And what else does it need? It needs this, which is an integer, and I believe that this is all that it needs, right? So we can just say was input valid and tries after blah blah blah, right? So our full comprehension is small again, okay? And we can continue like this. For example, we can go to this one, and we can say, okay, oh, this is actually the moment where he ran out of tries, right? So we can just say ran out of tries, right? So it's going to be over here, right? It's going to be a private def ran out of tries like this. And by the way, this decide what to do next, it produces an over here, right? It produces an IO of unit. Ran out of tries, same thing, produces an IO of unit. Let's join the line so that the full comprehension is over there. It actually compiles on its own, right? This tiny thing, right? Just a description of what's going to happen. We can also go a bit crazy with this, and we can say that this is the try again, right? Try again, right? It needs the tries after this iteration, right? So this is a private def. Whoops. Try again, right? It just has these tries left, which is an integer, produces an IO of unit, and it equals this. Let's say this. Okay, right? So this is exactly the same thing. Let's actually move it down. Yeah, so functional programming is a haven for people who like to refactor their code, right? So you can just read it top to bottom. Everything is really beautiful. What I'm going to show you next is going to be the reader monad. And I know that this video is kind of long, and we're actually by the end of this video. But if you understand the state monad, then you get the reader monad, so to say, for free. So I'm just going to go to state. I'm going to copy the entire thing. I'm going to paste this over here, and I'm going to call it reader. Okay, and now everywhere we're going to say state, we're going to say reader, and everywhere we say s, let me make sure that I do this. Everywhere we say s, we're going to say d. Let's see if it works. Yeah, maybe it does. So we're just going to say d. So the reader is basically the same thing as the state monad, but it just has some sort of dependency, which is contravariant, by the way, right? So instead of modifying state, it just works with a dependency, and now over here it doesn't produce a tuple with ad, just straight produces the a, right? I'm not even going to show you examples of the reader monad because it's actually very, very simple. I'm going to say a few words after this one once we actually finish typing it. Okay, so let's see. Create reader DAA. Okay, so we just need to do that. Let's see what else. It's a reader of DA, pure, create. Yes, same thing. Map produces a reader of what do we have? DB. Yes. Okay, so now we have some dependency comes in, and we're just using it over here. Now over here, it's not a tuple that comes back, it's just an A that comes back. So we're getting a B, and now we're just returning the B. Okay, and the same thing over here. What's happening? It's not an S, it's a D. D comes in. It's not a tuple that comes back, it's just an A that comes back, and we're using it over here. Now this is the trick. When we run it again, we use the same D, right? So it's just a dependency. We keep reusing it. Okay. So what it produces is just B instead of the whole tuple, right? And this is all we need to return it because we're throwing out the right part of the tuple. Okay. Flatten. Let's see. So some dependency comes in, being called like this. It just produces the CA. We run it again, also with a D, which produces an A. So we're producing an A like this. Let's see if it compiles. It should, right? It's a very mechanical transformation. So the reader monad is essentially the same as the state monad, but whereas the state monad is a bit more complicated, it actually transitions some state. This doesn't do anything with the dependency. It just passes it along. right? Which is why also the reader monad is sometimes used for implementing dependency injection in the functional world. All right, so during this series, you have seen the maybe monad, which is similar to, it's not similar, it's basically exactly to the option monad that is present in the Scala standard library. You have seen the IO monad, you have seen the state monad, which is a bit crazy, but honestly, if you spend a bit of time playing with it, then it's actually not that crazy. And then we learned also about the reader monad, which sits somewhere between the IO and the state monad. If you look at it again, right, so IO, it just starts with nothing but produces an A reader, it starts with something and produces an A, and the state monad starts with something, but it produces an A with the next something, right, with the next state. Now, I skipped the probably most obvious monad, which is list, or in fact, most, if not all, collections in the Scala standard library, they implement flat map and map. They might not be monads because they might not abide the very important monad laws, but flat map is doing what you expect it to do. So you can stick lists into for comprehension and mix them with the other things as well. One important thing is that composing monads is not so straightforward. There's actually an entire topic of monad transformers, but you need to know that there is an I believe implicit conversion from option to something like a list, and therefore you can mix lists with options in one for comprehension. I'm not going to show this to you because this is trivial, and I'm sure that you know this. Now, if you want to see all monads out there, just Google for something like list of monads, and I'm sure that you're going to find some Haskell documentation or maybe even Scala documentation. I actually haven't tried this. The noteworthy ones that you need to know, at least in the Scala world, are either. Also, there's try, which technically doesn't abide one of the laws, but it's still very, very, very useful. And also future. In fact, I'm going to show you a small example with futures. I might have forgotten some, but essentially in the Scala world, there are two major known functional programming libraries. One is called Scala Z, and the other one is called Cats. They're very, very similar, and in fact, if you have an entire project written with one of them, transferring it into another one is going to be very, very straightforward. Now, these are just the major libraries. There are also others that concentrate on some specific monads. For example, like for instance, there is Monix, there is FS2 streams, there is Zio. In fact, Zio these days actually mixes the IO monad with the reader monad a little bit, which allows for some really, really convenient things. And there are many, many others. All right, now let me show you futures real quick. And we haven't talked about asynchronous programming or about concurrency at all on this channel. So what a future allows you to do is it allows you to run a computation asynchronously, right, on a different thread, right? But as I said, we haven't actually talked about concurrency. So just take this example in. So we're gonna go to the interpreter, and we're gonna pretty much throw out everything. So I'm just gonna do this, and now it's gonna run an empty main. Okay, so we have an implementation of futures in the Scala standard library. So the first thing that we need to do is we need to import it. So we just go and we say import Scala dot concurrent, like this, right? So what futures need to do, they need some sort of thread pool, and it's being injected with an implicit parameter, right? So it's been injected as a type class. And by the way, this could be like if the Scala standard library was even more functional, this would be a valid use case for the reader model, right? So this is going to be a dependency that every future needs, right? So we're just going to say implicit val EC is the execution context dot global, right? So this is a thread pool. Okay, so now we can create one future, right? It's going to be a future of, and we're going to print out something. We're going to say this is going to be printed out in green, and we're going to say plus, come on, what's wrong? Plus, there we go. First future started plus console dot reset, like this. So now we're going to simulate a computation that needs some time. For example, we're fetching something from some remote server, for example, right? So we're going to have thread.sleep, and then we're going to copy that like this, and we're going to say first future finished, and what finished like this, and what we retrieve from the database or from this other service is just a number 5, right? So this is a future of it. Okay, so what we're going to do over here is we're going to say a print line is going to be printed out in white. We're going to say after first future. Okay, and if I run it already, this is what we're going to see. We're going to see after first future, and then we're going to see first future started, right? Because this is happening asynchronously. This is happening somewhere else, right? So we see this one, in fact, before this one, right? Because over here, 2 seconds will pass until we see this line. In fact, we don't see this line because the entire main dies before it finishes. Okay, let me just continue with the example. We're going to have the second one, so I'm just going to copy this one. I'm going to go down over here, right? and I'm gonna also do that. I'm gonna say after second future. So this is going to be f2. Okay, so it's going to be a future, and I'm going to say second future started. I'm just going to use yellow. Whoops, I'm going to use yellow over here, right? So the second future is going to be yellow. Let's say that it waits only for 1 second. Okay, and it produces a different number, right? So it produces a 10. Okay, so now we're going to have this third future, which we're going to use which we're going to produce by using a for comprehension, right? So we can say over here, say for, right? And now A comes from F1 and B comes from F2, right? Because it's a monad, sort of. Yield, okay? And now over here, we're going to say a print line console.read. Actually, it's going to be the same thing as over here. Let me do this. Put it over here. This one is going to be read, and there will be no waiting, right? So we let's imagine that we fetched 5 from some distant database, and we fetched 10 from Facebook, for example. And over here, we just need to make a calculation based on them. So we just need to calculate the result by saying a plus b, right, which is an integer. Right, so now we just need to return the result. Okay, so this calculation runs fast, obviously, right? So the performance or scalability heavy things that were happening in F1 and F2. Now we have all the data, and combining them together should go really smoothly. Okay, so now we can say after third future over here, after third future, and now we need to have some space for all of them to finish. So we're just gonna sleep for 4 seconds, and we're gonna say print line shutting down. Okay, so now if I save this, this is what's happening, and shutting down. All right, so what we see is after first future, and then first future started, and then after second future, and then second future started, and then after third future, and only then the second future finished, and only then the first future finished. And as soon as that happened, the what second future? Oh, hold on. No, hold up. There's the wrong print line somewhere over here, the third one. All right, let's do this again. This is exactly why I had the colors. Okay, so only after both of them finished, we actually were able to start the third future, which just calculated the result. It was finished, and after the whole thing, the main was shutting down. One of the common pitfalls of the futures is that because they start running right away on creation, if I convert them to lazy vals, this one and this one, then notice what's going to happen. The second future doesn't start until the first one finishes. Did you see it? Like only as soon as the first one finished, only then the second started. Let me do it again. Finished, started. Right? And this is happening because if you write the for comprehension in the regular flat map style, right? So if we just go here and we say f1.flatmap, and this is going to be the A, and this is going to be f2.map, and this is going to be B. In fact, let me even go further and do it even closer to the thing. I'm going to say that this is a flat map of oh no, this was already correct. B. Okay, so now we have A plus B, and let me go here like this. Okay, so this is the whole thing that happened there. So it's not just A plus B. Okay, so if I remove that, and now you're going to see, oh yeah, I forgot the B. Hold up, B, arrow to the right, arrow to the right. Okay, so we have A and B, and now you see over here that F2, it's a lazy val, so it's not being created before A is already available, right? So I showed you this was lazy vals, but basically, the common practice says don't create futures inside of the for comprehension. Always create them before. All right, so that's pretty much all I got for you today. This is going to be the last video, as already announced, in this Monad series. But as I said, in the future, I will be adding even more videos to this playlist in the future. There's one cool thing that I forgot to tell you, right? So now you finish this Monad playlist, and monads are a gateway to understanding so much more, so many functional constructs. In fact, they're lurking everywhere, and you might not know about them if you don't understand monads. In fact, let me show you this. If I go online and I look for promises in JavaScript, so I say promise JavaScript, right? The first thing that we find is documentation from MDN, right? Let me make it a bit bigger. Okay, so in JavaScript there is no distinction between in fact I didn't explain this before. In Scala there is a distinction between a promise and the future, and the promise is like a write handle, right? So you can write something and then you get the handle, you get your val, and the future is sort of connected to promise. It's the read handle to the value that might not be computed yet. Now in JavaScript, instead of this distinction between promises and futures, you just have the promises, right? So the promise is both. So what you see here is an example that creates a promise that in the end produces a string called foo, right? So this is a promise. But the example then calls then on promise and console logs. And when I see stuff like this, like I'm trying to stay positive, right? Usually in my videos, but when I see this pisses me off, because a promise is a monad and then is actually a flat map. And let me show you this. It would have been so much better if this example, for example, if it would go and produce a 5 over here, right? And now instead of side effecting over here like a boss, instead of console logging value, I mean, people know how to console log shit, okay? So instead of this, what if it would do return value plus 10, okay? Now this is now a var promise 2, okay? And now over here, because this is flat map, it's called then, but this is flat map, just trust me, okay? So now over here down there, we can go and we can do another flat map, sort of like our for comprehension. We can just go and say promise 2 dot then, and by the way, these days JavaScript also has lambdas, so anonymous function, they call them arrow functions. So if the value comes in, we can just console.log value out. Let's see if I made any typos. If we run this unexpected number, so which means that I made some error. Oh my god, I'm so silly, there's a space over there. Jesus. Okay, there we go. Run. So this is what we have, right? So this essentially is flat map. Sorry that it took so long. It took me like almost 2 hours actually to record this, so I'm kind of falling asleep here. So we got our first promise. We are producing the second promise by calling flat map, right? I'm not sure if JavaScript has full comprehension. No, it doesn't, right? It doesn't have full comprehension. All right, so yeah, and this is how we're producing the second one, and this is the result over here, right? So now, yeah, so it's kind of unfortunate because the JavaScript world is sort of behind these functional constructs, and it would be kind of cool, like if the first documentation that you find would actually show you like the powerful thing, because this is not super complicated to understand, right? Even if you don't watch like all my monad videos, or if you don't understand monads at all, right? Nothing here screams monads if you don't understand monads, right? But understanding this example, I'm sure every beginner could understand this, right? That somehow this value is being passed over here, and then 10 is getting added, and then you do then again, and only then you do console log. Any case, I don't want to rant anymore. Let's go back to my VM. All right, let me say just the last words, even though I'm blabbering at this point. If this is the first time that you have encountered monads and you finish the series, now you might be thinking that monads are the best things since sliced bread, which is, it's a common thing. Like every time you learn something new. But as I mentioned so many times already in my videos, there is nothing perfect in this world. Everything has trade-offs. For example, monads they sometimes have issues with stack safety. Right, there are solutions to that, but it's just like things that you need to be to be aware of. For example, monads don't compose well, but there are also solutions in some cases for that as well, and so on. And as I already mentioned, there will be more videos about monads and functional programming in the future, but as of right now, I just really want to come back to the homegrown collection series as fast as possible. As always, use the right tool for the job. It's been Vlad, devinside.com. Like this video if you did, subscribe if you want to improve the developer inside you, and if you find my videos valuable, consider supporting me on Patreon, and most importantly, take care.